So, let us also look at Gibbs sampling now and look at what is the key difference. It has many of the aspects of the randomized motive search algorithm, but it has certain things that are the key difference that is highlighted in this slide. Okay. So, if this blue is your current set of motives, randomized motive search can use the current profile and then figure out what is the best k-mer, profile most probable k-mer in each of your input string, and may update it to this new set of k-mers. In this case, k is 3. So, 3 mers in these strings, which are these red ones. Okay. And so, it will change, so it may change all k-mers in one iteration. Okay. But what Gibbs sampler does is that it chooses a random sequence. Okay. So, in this particular case, the second sequence, it will freeze all the others, and in one step of the algorithm, it will only change that sequence as k-mers. Okay. So, this ATA has a certain probability of being generated by the current profile, but then you will look at all the other k-mers also, and then this red TGT has, let us say, the highest probability of being generated by the current profile. Then it will switch this ATA k-mer to TGT, but all the others are continuing to be the same, they are continuing to be in the same blue locations. Okay. And that is the main difference between randomized motive search and Gibbs sampler. You change all the motives, all the k-mers when you are updating your motives in randomized motive search, but in Gibbs sampler you only change one at a time. Okay. And that turns out to have certain advantages, because if you have a nearly correct motive, where almost all of the motives you have found the actual truly implanted motives, but in one or two sequences you do not have the correct motives, then the Gibbs sampling is a more conservative approach, it is a more cautious approach to update your profile. Okay. Let us just look at an example, the same example how Gibbs sampler would do. Okay. So, you randomly select your motives which are in bold, and then your blue is still your ground truth. So, it is exactly same as before. So, you have randomly implanted the blue motives, right, and then the initial set of motives that the algorithm has figured out is in the bold. Okay. And it so happens that the final sequence, the blue and the bold are coinciding. Okay. So, we are lucky with the final sequence, but in all the other sequences, all the other 4 sequences, we have not found the correct implanted locations yet. Okay. Let us see if Gibbs sampler can figure it out. Okay. The way that Gibbs sampler works is it uses randomness in multiple places. Okay. So, it is not just in the initial set of motives that it randomly select, that is the same as randomized motive search, but it also randomly picks one of these 5 sequences. So, in this particular case, it has tossed a coin or a dice that has 5 sides, and then 3 comes up, then the third sequence is being blanked out. Okay. And then you look at the motives only in the other sequences. Your motive matrix will not have all the T strings, it will have T minus 1 strings now, right. So, the third one is blanked out, and now using the rest of the motives, right. So, this bold ones TAAC, GTCT. So, TAAC, GTCT, you have ACTA, that is ACTA, and AGGT, right. And then once you have this motives matrix, you can construct your profile in the usual way. You can look at what are all the count matrices you have, like 2 A's here and then no C's here. So, you have 2 0 and then you have 1 G and 1 T here. So, you have 1 and 1. Similarly, for all of these columns, you can update your, can compute your count matrix, normalize it to get your probabilities, which is your profile matrix. So, once you have this profile matrix, then you can look at this deleted string, and then you want to pick a k-mer that matches this profile matrix the best, right. And so you can try to use this profile most probable k-mer, but Gibbs sampler is different. Here also it uses randomness. Okay. So, what it will does is that it will compute the probability of all of the k-mers in this deleted string. So, there are 7 k-mers here, 7 formers here, CCGG, CGGC, GGC, G and so on, right. So, the CCGG, CGGC, GGCG and so on, right. So, there are 7 of these k-mers. It will find the probability that each of these k-mers can be generated by this profile matrix. Okay. And then once you have all these probabilities, then it will sample one of the k-mer according to these probabilities. Okay. So, or specifically you roll a 7-sided die with probabilities of the sides proportional to the probabilities of these 7 k-mers. Okay. And then once you select that, then that will be your updated k-mer in this third string. Okay. So, in this particular case, there is only GCGT with a non-zero probability. So, that will definitely be selected. So, then you have GCGT, but if there are multiple non-zero entries, then you will just randomly choose one among them with weights proportional to the probabilities of those different non-zero entries, right. So, you have GCGT which is being added, and that will be updated here as this GCGT. Okay. and then you repeat this whole process again by randomly choosing another string and so on. Okay. So, this has been updated. So, then the third string schemer has been updated. So, you only update one at a time. Okay. And this iteration again, right, you will choose one other set of say one other sequence at random. Maybe instead of the third sequence you may use you may select the fourth sequence, then you construct your profile, and again there is another randomness used here on among these 7 k-mers, right. So, 7 4-mers, you just choose one of them at random proportional to the probabilities that you have computed using this profile matrix. Okay. So, it is worthwhile to also look at where randomness is used in Gibbs sampler. So, Gibbs sampler is a more randomized algorithm than randomized motive search. The reason being that randomized motive search will only use randomness at the very first step of the algorithm. It will randomly select motives at the very first step of the algorithm. After that, everything is a deterministic process in randomized motive search. Okay. But in Gibbs sampler, randomness is used in multiple different time points throughout the algorithm during every iteration, right. So, the initial, like in the other algorithm, it will initially select a set of random motives in bold. So, that is one place where it uses randomness. And again it will use randomness in the very first step where you decide which sequence to blank out, right. Here it is the third sequence, but in the next iteration it may be the second sequence and so on. So, that is another place where randomness is used. And more importantly, the third place where randomness is used is that if you look at all of your 7-mers in the deleted string, right, and then you calculate your probabilities, you do not choose the profile most probable k-mer, you just choose a k-mer with weights that are proportional to these probabilities. So, you just sample from the set of k-mers. So, you do not have to necessarily pick only the profile most probable k-mer, something that is not optimal, that will have somewhat lower probability can also be selected. Okay. So, to illustrate Gibbs sampler using the previous example that we have seen before, let us look at this table again. Previously we said that this table looks at for a given input sequence, right, all of the k-mers. In this particular case this k-mer CTA TAA, right, all possible 6-mers, right. So, this is one 6-mer, this is another 6-mer and so on, right. So, it looks at all of these 6-mers and then it calculates the probabilities, right. If you want to focus only on the most probable profile most probable 6-mer, then you will only be picking this AAACCT, right. That is what the randomized motive search algorithm will do, right. It will only pick this 0.03336, right. But then you may want to pick 0.0299 also, right. So, this particular k-mer AACCTT, right, this particular k-mer also has a close enough probability, maybe not optimal, but close to optimal. 0.0299 is still close to 0.0336, right. So, that should also be given a chance sometimes. Similarly, the final one is low probability, yes, but it is still non-zero, and so this TTA CAT should also be given a probability, should also be given a chance sometime, right. And Gibbs sampler gives these chances. It does not just focus on the largest entry here, it looks at all the non-zero entries and then it will choose one among them. It will sample from them with weights proportional to these different probabilities. Okay. This is the pseudo code of this Gibbs sampler. Again, all of the places where randomness is used is highlighted here. So, you form motives by randomly selecting a k-mer in each sequence. You randomly choose one of the selected k-mers from the removed sequence, right, and then remove it from the motives, right. So, this is what forms the removed sequence, right. And then similarly, finally, the randomness is in you roll a dice with n minus k plus 1 side, right. That is all the k-mers in the deleted sequence, and then you want to figure out what is the probability of all those k-mers, and proportional to the probability you sample one of them, right. So, you are not just choosing the profile most probable k-mer, but you are sampling from all of the k-mers in the deleted sequence. Okay. And all of these different steps are repeated. I will not go through every step again, we have gone through it in a pretty much detail using the example that is seen in the previous slide. Okay. Now, let us just look at, there is one final point that we want to address. Okay. There is this persistent problem of zeros, right. So, even though Gibbs sampler allows kind of different k-mers in a sequence to be all chosen and not just focuses on the profile most probable k-mer, the problem is that if you have a lot of zeros, it can never choose zeros there, right. And then so, if we ignore all of them, we do not have a 7-sided dice, we really have a 1-sided dice that always shows up GCGT in these kinds of cases, right. So, zeros are not really helpful in our algorithm because it really robs Gibbs sampler of one of its strengths. So, the Gibbs sampler actually allows even suboptimal k-mers in a string to be chosen, but if many of them are zeros, then they can never be chosen even by Gibbs sampler, right. So, can we try to handle these zeros, can we just remove these possibilities of zeros, okay, and that is what we will look at as a final point to address, okay. And the zeros, this probabilities of zeros or 1, right, have had a history already, that people have not preferred to have probabilities of zeros or ones, okay. They, in real world data analysis and data inference, data based inference, you would not want to deal with 0 probability or 1 probability, an event that never happens or an event that always happens, right. And Cromwell has already made that appeal to the Church of Scotland. So, I will not get into the details. If you are interested, you can look into the book to know the history behind it. But not just Cromwell, others have also talked about 0 or 1 probabilities, especially in the context of what is the probability that the sun will not rise tomorrow, right. And you may see that, I mean, all the years that you have been alive, right, you have seen that every day the sun rises, and so you can say that it should be, probability should be 1, right. But we should always allow the possibility that it may not arise, I mean not rise tomorrow, right, because I do not know when. So, billions and billions of years going forward, the sun will eventually die down of all its gas that it has, and then at some point in time it may also not rise, right. So, we will have to allow the probability, we have to leave a little probability that the sun will not rise tomorrow, right, and that is where the concept of pseudo counts comes in. It is closely related to Bayesian analysis also, but we will just look at it without any of those terminologies and just simply say what pseudo counts are, okay. So, Laplace was calculating the probability that the sun will not rise tomorrow, and then he said that it should not be 0 based on all of our observations. If we have seen that it has risen every day for the past 5000 years, then it should be 1 in some very large number. It should be close to 0, it should be some small number, but it should not be exactly 0, okay. And how did he come up with this estimate? And his estimate at that time was ridiculed, but now we know that pseudo counts are used to derive that estimate, and then that pseudo counts actually make randomized algorithms such as this Gibbs sampling based algorithms work better than without using pseudo counts, okay. So, this will handle the zeros in the count matrix that we had, okay. So, Laplace had this particular scenario where an experiment was repeated n times and then you see s successes, okay. So, then you want to know what is the probability that the next repetition will be a success, okay, and the way you write it out in a probability is that you have the outcomes of these n experiments, each one of them is 0 or 1, 0 is a failure, 1 is a success. So, if you have seen s successes in the first n trials, I want to know what is the probability that the n plus 1th trial is a success, okay, experiment is a success. Typically, given that we have observed n, we have run n experiments and then we have observed s successes, we may think that this is s over n, okay. If we have it this way, then the probability that the sun will not rise tomorrow will be 0 over whatever the number of days in the last 5000 years we have observed the sun to have risen, right. So, then that will give you 0 probabilities, right. So, but if you add pseudo counts, we are just always allowing the possibility that before I make any observations, I am going to allow 1 success and 1 failure, okay. Those are these pseudo counts. S and n are the counts, but the pseudo counts are this 1 and 1, okay. I am going to allow 1 success and 1 failure, right. And so, instead of s over n, I am going to say that there are totally now I have done n plus 2 experiment, because I have added the pseudo count of 1 success and 1 failure. These are the very first 2 experiments that I have done, okay. And then combined with the n experiments that I have actually done. So, there are these 2 dummy experiments I have done, and then the n actual experiments I have done. Then I have s successes observed in these n experiments, and then out of these 2 dummy experiments, 1 is a success, 1 is a failure. So, I just add 1, okay. So, instead of s over n, a better estimate is s plus 1 over n plus 1 plus 1 or n plus 2, okay. And these 1s and 2s are the pseudo counts, they are called as pseudo counts, okay. And this is what Laplace said and how he calculated the very small probability that is not equal to 0 for a sun to not rise tomorrow, okay. And let us just see how it will work in action. So, let us see what Laplace would do to get rid of zeros in this matrix, and the idea is very simple. You just add plus 1 to all the entries in this count matrix. So, even before you observe the actual data, which are all these motifs, you just start with a prior assumption that, right, that each of the columns you have observed 1A, 1C, 1G and 1T, and then on top of that whatever you are newly observing will be added. Okay. So, here is the plus 1 that is being added here. So, you have already you start out with an all ones matrix, that is your pseudo count, and the assumption there is that a priori you just think that every column you already have 4 experiments that are done, and then in each of those experiments you have observed an A, C, G and T, right. So, in one experiment you have observed an A and another a C, another a G and another a T, right. And so, then you have on top of that, then you can add your 2 A's here, that is 2, 0, C's here 0 and then G and a T, right. Now, the C that is being a 0 is no longer 0 because you have the pseudo count of 1. Okay. Now, once you have that, then you can compute your profile matrix, you can update your profile matrix. Initially you had 2 over 4, 1 over 4, 1 over 4 and 0. Now, you will have 8 in the denominator because you have added these 4 more pseudo counts, and then you will have 3, 1, 2 and 2 here, right. And so, the zeros here and the 0 here are removed. Okay. And because of that, now if you update your probability of the different formers in your deleted string, the third string, right. So, then all of the zeros that were before, because of 0 entries here and here, right. So, here and here will now be non-zero, and so all of this will get updated in 1 in 1024, 2 in 1024 and so on, right. And still the highest probability is still this GCGT string, but then you have these non-zero probabilities for all the other things. So, this was 6 over 1024, this is 3 over 1024, this is 4 over 1024. So, you will not necessarily only select GCGT, sometimes based on the random coins throws by the Gibbs sampler algorithm, you can also select this GTTA, which is 4 over 1024, or TTAG, which is 4 over 1024, or for that matter any of the other k-mers in this particular deleted sequence, okay, this third sequence that was deleted, right. So, now rolling a 7-sided dice makes a good sense, because there are 7 formers in this deleted string and all of them have non-zero probabilities, and so these die can be loaded in that way, and so each of the side has this probability of 1 or 2 or 2 or 6 or 3 or 4 or 4 in 1024, right, rather than just focusing only on this non-zero number of GCGT that we had before. Okay. Now, we have 7 non-zero numbers, and so no zeros. So, then you will choose a new starting position in this deleted sequence based on rolling the die, and it need not always be GCGT, it can also be other k-mers. Okay. So, let us see 1 or 2 more iterations of Gibbs sampler using this kind of new technique of avoiding zeros, okay, the pseudo count techniques of Laplace. So, you are again this is your current setup here, right, with the deleted third sequence you have chosen GCGT, right. So, now you have this this set of bolds TAAC, GTCT, GCGT, ACTA and AGGT. Now, you randomly select the first sequence to blank out or delete, and then you construct motifs matrix from the remaining sequence motifs, right. All the bold letters are now aligned together. You compute your counts matrix, but you make sure that you add 1 pseudo counts, so that there is not too many zeros. Then you normalize that, right, and then you calculate your probabilities in the first string that is being deleted for all the k-mers in the first string. Okay. Now, you have 2 in 4096, 2 in 4096, 72 in 4096 and so on. Okay. Then again using this you roll a 7-sided dice with all the faces coming up into these different k-mers according to these different probabilities, and you choose a new starting position, and it ends up being ACCT. Okay. So, this is being chosen. Okay. And again we have already seen that this is now aligning with the actual implanted location, right. So, this ACCT is being chosen, then you can keep on continuing that. Okay. Now, you can delete the fourth sequence and so on, and keep repeating your pseudo count, creating your profile using the pseudo counts, and then choosing the random k-mer according to these probabilities, right, generated by this profile matrix for the fourth sequence. Okay. Now, that has that you kind of focus in on ACGA, which is one of the blue locations, right, it is a ground truth location. So, you have the first one, you have the last one is correct, the last but one is correct, the third one is correct. So basically you are like quickly converging on the correct implanted locations. Okay, that's what is given here. So we have already captured 4 out of the 5 correct k-mers, and if you repeat it one more time or a few more times, you will almost surely find all the implanted motifs, okay, including in the second sequence that we have not found so far. So that completes our discussion of the Gibbs sampler algorithm, and let us look at one more slide on what are some of the remaining challenges in this particular field. Okay. So the challenges really comes in when you have small motifs, right, and then long sequences. This means that k is small, okay, and then you have long sequences, which means n is very large, okay, and then you have not very many number of sequences, but a very small set of sequences. So sample size is small, okay. So sample size is not enough. So sample size is small, meaning t is small, okay. When all of these in different combinations come together, then this kind of needle in a haystack problem becomes very prominent, and then it will be harder to find a good motif or a good pattern that is represented in a set of input sequences, t input sequences. Okay. And what can we do about it? So we can try to see if there are computational algorithms, but there is a reason that we are in the field of bioinformatics, where both informatics and bio has to play together. So there are experimental techniques which can really reduce the size of the sequences, right. So initially you may have to look at like 1000 nucleotide long strings that are upstream of your target genes, but if you do certain experiments like ChIP-seq, that can actually reduce your length of the sequence n from n equal to 1000 to n equal to 100, right. Now when n has become smaller, then it is easier to find a k-mer in the smaller string that you have, right, and if you have enough of your t strings that are provided. So this ChIP sequencing can also increase t, right, the number of sequences t. That can also go up in ChIP-seq because you are looking at all the positions in the genome where a particular transcription factor binds. That is what this ChIP-seq or ChIP sequencing experiment does, right. So you won't be looking at some 20 genes or 10 genes or 25 genes that you have hypothesized to be bound by the same transcription factor. You can run this experiment for a single transcription factor and then find out the putative binding sites of this transcription factor across the whole genome, right. So you will have a lot of sequences t where the transcription factor binds, and each one of the sequences is not 1000 long, each one of them is 100 long, because you can align the ChIP sequencing reads back to the genome and then look for peaks of length about 100 where many of the ChIP-seq reads have mapped to the reference genome, right. And so your n has also now come down, right, and the k can be whatever the k value that is the best works for that particular transcription factor, right. By decreasing n and increasing t, by decreasing the size of each sequence and increasing the total number of such sequences, the sample size, ChIP sequencing will make this problem of finding motifs to be a bit easier, right. So ChIP sequencing combined with computational motif discovery. Okay. So this is a true marriage of an experimental technique and computational analysis to better find regulatory motifs that transcription factors bind to figure out to do the different functionalities of the cell, right, and that we have seen ranging from the clock genes to how TB goes from a dormant state to an active state or back. Okay. I hope it gives a good sample of how experiment and computation can come and work together. With that, we will end this particular session. Thanks.